Hi, hello, good evening, everyone. Uh, am I audible? Can anyone confirm if I'm audible or not? Oh, thank you. Um Once again, hello. I am Pravalika. I'm a PMRF and a PhD scholar from IISc Bangalore, and I'll be your TA for this session. And today's topics we'll be covering linear algebra, solving linear equations, distances, and hyperplane and half space. If time permits, we will go to that as well. But if time is not sufficient, then it's better. It's more of theory than what I can show on R and eigenvalues and eigenvectors. Okay. First and foremost, before I begin the session, I just wanted to let you guys know that this session is being recorded, and 3 to 5 minutes break will be given after every half an hour, and 10 minutes break will be given every 1 hour. Also, it will vary according to your needs. And if you would like me to cover more topics in the next session, please let me know at the end so that I can make note and I can prepare accordingly and I can teach you guys. And also be respectful to one another and towards me and during the entire session. And if you are not following the rules and being respectful for any with anybody, I can directly remove you guys, and I don't hesitate on that. Okay, so with that, I'll start the session for today. So sorry, was I not audible at all so far? Okay. I hope it should be fine now. Okay. In case if it happens again, just please let me know. Okay. Thank you. So I'll just start over again. Okay. So as I was saying, linear algebra is like a cornerstone for many data science techniques and algorithms. And imagine that data is like a vast landscape. Okay. So it is basically raw and very, very unstructured. And linear algebra is like a tool that will help us transform this landscape into a structured and navigable terrain. Okay, it's like giving you a compass and a map for your data exploration. So why exactly is it crucial? It's because almost every data science problem can be framed as a linear algebra problem. So from understanding relationships between variables to making predictions, linear algebra is a language your computer will speak. We'll just start with the basics. So we'll explore some vectors, matrix, and their operations, and you will learn how to represent data using these structures and how to manipulate them to extract valuable insights. So linear algebra. Okay, let's get started. So I'll just give a basic example for now. Okay. So, okay. So imagine you need to buy some apples, bananas, and bread. Okay. Let's say apple, bananas, and bread. Okay. You went to a grocery store and you wanted to get these. And let's say, hypothetically, that apples are two, each one is two, and bananas are 1 rupee, and bread is like 3 rupees. Okay. So if I want to represent this in form of a vector, I can write it as 2, 1, 3. Okay. So now, in case if I get 3 apples and 2 bananas and 1 bread, then I can represent that vector as 3, 2 and 1. Agreeing with me? So now if I want to get the total cost, what should I do? What should I do with these two vectors? Now I have both these vectors. So what exactly should I be doing? Um, yeah, right. So you have to multiply this first vector with the second vector, right? So let's do that. So this is what 1, this is 1 cross 3, and let's write this as, okay, we'll just transform this and we can write, right? Agreeing? So what will this make? It will make 11. So the total cost for me is going to be 11, right? So now, so this is something like a basic. So this is just for vectors. I mean, okay, this is just for vectors. Now, let's go a bit forward and then let's say you are a store manager and you wanted to take 3 products. Let's say it as A, B, and C. Okay. So you want to know how many of each products you sold last week and this week. So you just want to compare between the previous week and this week. Okay. Let's just say, we'll write it like this: A, B, and C, and last week and this week. Okay. So maybe let's say last week 100 of product A were sold, and this week maybe 120. And last week B products 80 and let's say just 95. Okay. And C, let's just say 50 and 60. Okay. Now I basically have a matrix, right? So this matrix is going to give me a clear overview of the sale. So I can easily compare between this side and that side. The for each product, what is being sold and how much is being sold and everything. And with this, you can calculate the total revenue, uh, similar to the previous one, right? And you will have the prices and all of these things. Okay, clear so far? Okay, so let's just see some basic operations that you guys already know. But just in case, so let's just say we'll do some addition of 2 matrices. Just say 1, 2, 3, 4, 5, 6 plus 3, 2, 1, 1, 2, 3, something like that. Okay, so this is going to give 1 plus 3, 4, and 2 plus 2, 4, 3 plus 1, 4, 4 plus 1, 5, and this 7, and this is 9. So similarly goes for subtraction. Please don't scold me just because I'm going too basic. But just in case, I just wanted to continue everything. Uh, I can't understand. Can you repeat one more time? Which one exactly should I repeat? Is it addition or the part before that? Okay, I'll just say it again. Okay, for matrix, let's just say A, B, C are 3 products. Okay, some products with the name ABC, and we are looking at a store, and in that store 100 of product A were sold last week and 120 of product A were sold this week, and similarly A, B, and C. Okay, so similarly A, B, and C. So now we are representing this in form of a matrix. Okay, So we are basically comparing the sales of these ABC products from last week to this week, and also we can uh, look at how much these products are being sold. Like now, if you look at this whole part, you can just directly say that 100 are A. So basically, A is much sold compared to B and C, and C being the least. You can say you can come to such conclusions if you are writing this in form of a matrix rather than something like in Word. Okay, I hope I'm clear on that part. Okay, so additions also, we are having two matrices here. So in addition, we do element wise addition. So the first element will be added with the second element, and so on and so forth. Okay, so let's just look at multiplication. Okay, we'll just take some basic without numbers, so that will be easier. D, E, and F. Okay, so for multiplication, we go row wise for this and column wise for this. The first element in this vector and the first element in this vector we'll multiply A and D, plus then the second one and this second one. So it's B and E and C and F. So basically you are multiplying element wise and then adding the whole thing. So if you are having more, then you are going to get more things as a matrix. Okay, and just as a small recap, uh, let's just say I have a matrix of m cross n, and I have another matrix of n cross some x. Okay, if I have to multiply between both these matrices, I should make sure that the number of columns in matrix A and the number of rows in matrix B both are the same, and the resulting matrix will be these two. Okay, m cross n, sorry, x. Okay, so that is a quick recap that I wanted to give. Is there anything else I wanted to say? Yeah, and determinant. And let us say I have a matrix 2, 1, 3, and 4, and I want to find the det of this. This is A. Then det of A is equal to cross multiply these two. So 4 cross 2 minus 3 cross 1. Okay, which is going to be 8 minus 3, which is going to be 5. Okay, so similarly determinant is calculated for whatever number of square matrices we have. Okay, uh, I hope I'm okay with the recap. So now I just wanted to go with representing image as a matrix. Okay, what's the application for finding determinant? I'll tell you why I'm explaining determinant once again here. So as we go forward, we will look at some of those again. Okay, can't we write ABC as attributes or as columns? Yes, you can write. It's your representation. You can represent the way you want. But then again, I'll come to that as well. So basically, we take the rows as sample points. Okay, so that is why I have represented these here last week and this week as columns and ABC as rows. I'll come to that. Okay, so image as a matrix. Okay, so you imagine you're looking at a beautiful landscape. So every detail and the color and everything that is captured is in a single glance. So if you look at it in a digital world, how you represent this image is using mathematics. Okay, so that's where the matrix come in. So essentially, digital image is a grid of pixels. So you can see here. So we have an image. Okay, it's a handwritten image. Okay, with the number 8, and if I am looking at it in form of a matrix, I have some specific values here and there, if you can see it clearly. So 2, 15, 0, 0, 11. So it is representing something to me, right? So this is how a digital image is there. So these are called pixels. So this is whole thing is a grid of pixels. So each pixel has a color value, and we can represent this grid as a matrix. So where each element corresponds to the color value of a pixel. So, for example, a black and white image can be represented as a matrix of numbers where each numbers represent the intensity of the pixel. So, from black being 0 to white being 255. So, where a color image would have three matrices, color image would have three matrices, RGB image. I hope you have heard of that, right? So, R stands for red, G for green, and B for blue. So if you are looking at a black and white, we just have black and white, and RGB, we have all the three color channels. Okay. So we can just adjust these brightness, contrast, saturation by performing some arithmetic operation on this matrix element. Okay. So what can we do with these matrices? Well, we can do so many things like image filtering. So these matrices can be used to apply some filters like blurring, edge detections, sharpening, etc. So we can also do image compression. So sometimes when you are applying your passport size photos to some portal, for example, Gate, it might tell you your image size is too big, like compress it. So such image compressions can also be made using some arithmetic operations in on these matrix elements. Okay, um, and then so yeah, so each pixel has some values like this. Okay, each pixel has some values starting. Okay, it's from 0 to 255. Okay, 0 being black and white being 255. Okay, and yeah, and matrix data, we show this matrix data, we have this matrix as two things, rows and columns. Okay, the rows being the data points or the samples, and the columns being variables. Okay, as I was telling you guys earlier, so we had ABC products here, and last week and present week sales, sorry, week, we had some values like this, right? So if you can see the column, this is not a constant, it is the one which is varying every time. So we are representing the columns sorry, the variable in the columns, and then the data points as in ABC as the rows. Okay, and yeah, also linear algebra usually they take as a complete semester course, and I have to combine everything into, I'm so sorry, just give me a second. um, you can also react, that is okay if I'm audible. Yeah, thanks. Okay, let's continue. Sorry for that. So to find the number of independent variables, we also want to find the independent number of variables. As I was saying earlier, linear algebra usually they take as a complete semester course, but rather now I have to combine everything in a 2-hour lecture. So I'm skipping most parts. I'm only covering the parts which are necessary for this particular R code that I'm going to share after some time. Okay, so I'm just giving some basic only right now. How does the part of matrix can be written in coding? Yes, I will also go to the coding part. So first I want to cover some theory part and then go to the code so that it will be clear. Okay. Okay. So to identify the number of independent variables, we use a concept called ranks. So rank of the matrix. So it is defined as the number of linear independent rows or columns that exist in the matrix. Okay. So we'll just take an example. Let us say that you are analyzing some nutritions of some food, different food contents. Okay, so you have a table like what all you look at: fats or proteins, carbohydrates, and various foods, right? So let's just say I have foods called ABC. I'll just change the color. I have foods like ABC, and then we'll see proteins, carbohydrates, and fats. Okay, so let's just say 3, 2, 1 and 4, 1, 2 and 3, 2, 1. Okay, so the rank of a matrix is the maximum number of linearly independent rows or columns. So it is essentially telling us how much information the matrix carries. So in this example, the matrix of this is 3, assuming all the foods have different nutritional profiles. So this means that each each food is not depending on the other thing, so it is completely independent information about the food. So basically we have the rank is equal to 3 here. Okay, how to calculate rank and all of that, I think it's already there on NPTEL video lectures. So if you want to do it manually, you can also check out some videos on YouTube as well. Okay, so for now I just want to skip it. Okay, so I'll just write it here. So number of linearly independent variables, right? Okay, so then we will cover the concept called null space. So the null space of a matrix is the set of all vectors that when multiplied by the matrix results in a zero vector. So it represents the redundancy in the data. So uh, when it is multiplied, okay. So since we are having no, since the rank here is 3 and which is also equal to the number of rows and columns, we don't have any null space here. So it would be an empty one. And also we have something called as rank nullity theorem. So it states that the rank of a matrix, okay, rank of matrix plus the dimension of its null space is equal to the number of columns. Yeah, just hold on a second. So null space is basically a set of all vectors that when you are multiplying this, multiplying it with this particular matrix will give you a zero vector. So it is basically like AX is equal to 0, where A is the matrix that you are having and X is this null space. Okay. Can repeat null space with examples. I'll show you the code now. Okay. I hopefully in the code you will understand that part. Okay. Is it visible? Yeah. Okay. Thank you. Okay. Let's start with some basic example. Okay, we are using a library called as a matrix here. Okay, so I'm directly calling the library here, but in case if this is not there, you can, in case if it's not there, you can go to tools, install packages. Okay, then this comes up, and there you can type in the word matrix, and then you can directly install. Okay, or you can also write this uh, this code install.packages, and in double inverted commas write matrix. If you run it here itself, then you will be able to install the package. Okay, so once that is done, you just have to control and enter for that line to run. Control plus enter. Okay, then the library will be loaded. I hope all of you have remembered this control plus enter, that line running from last class, right? Okay. So let's create a matrix here. Just a sec. Okay. So the same matrix that I have shown you, I have written it here. Okay. So I have 2, 4, 3, 3, 1, 2, 1, 2, 1. So it's basically total nine. Nine numbers I have. So it, and I told I want 3 rows. N row represent the number of rows that I want. Okay, and how I want to stop divide it. Okay, so it's basically like I want it by rows, so 2 4 3 3 1 2 2 1 2 1, like that. Okay, and then now I have added something called as list here. Okay, so I'm saying I want on one side food A B C, and on the other side I want proteins, carbohydrates and fats. Okay, let's run this and see how it works. Okay, and here it is. So I have something called as food A, food B and food C, and proteins, carbohydrates and fats in the representing the column names, and food A representing the row names. Okay, is this clear? Is it clear so far? Yeah. Thanks. Okay, so now let us say I want to know the rank of the matrix. Okay, so as I was saying earlier, rank is the number of independent variables that we have in that particular matrix. So calculation of this rank and everything, please, if you want to do it by hand, please check it on internet. Okay, sorry, I have done it more times. So it has given me the rank of the matrix as 3, right? So it means, and the rank of the matrix is 3, and the number of columns that I have is also 3. So the rank and the independent variables, the columns both are the same. So which means that there is no null vector, null space that I have in this uh, uh, particular matrix. Okay. So in R, there is no direct function to calculate the null space. So as I was saying earlier, since we don't have null space for this particular matrix, we can try and check if at all R gives us any null space or not. Okay. So this is some code that we are writing. So QR basically gives, if you want to look at QR, you can just say, in the console, just give a question mark. In the console, just give a question mark and give QR. Okay, so this QR decomposition of a matrix. So you can just read the documentation here. Okay, so this is a bit complicated to calculate this null space based on this. Okay, uh, I'll explain null space again with an example. Just hold on. Okay. Uh, yeah. So you can just continue all of this, and then you will the null space here is nothing. So 1 to 3 is just the row numbers, and apart from that, I'm having nothing here. So which means that the null space does not exist for this one. Okay. Uh, and then let us now I'm running this n and I'm storing the number of columns of this food data matrix into a variable called as n. Okay, so then I want to check verify the rank nullity theorem, so which means that the rank of the matrix plus the number of columns of the null space should be equal to the number of columns of the actual matrix. Okay, so if I run, then it is showing the rank plus nullity is equal to 3 plus 0. So the rank is 3 that we already know, and nullity means the null space, which is 0 for us and which is equal to 3. Okay, so yeah, clear till now. You can just take a 5-minute break since it's 6:30. I'll continue back again. Okay. Can we continue? Yeah. Okay. So as I was saying, so if we are taking a matrix or a vector and we are okay, we are supposed to take only a vector. So if we are taking a matrix and we are taking a vector, and if it is multiplied, it will result in a zero vector, which is, let us say, I have a matrix called A, okay, and the null space, let us say it as X, okay. The multiplication of these two should give me a zero vector. So AX is equal to 0. For example, uh, let's take 2 1 1 2. Hopefully this should give, hopefully this will give me something. Okay, I'll do some operations here. This one is R1 R2 C1 C2. Okay, I want to make sure that this becomes 0. Okay, so in R2 X and Y. Okay, so I'll make R2 such a way that R2 minus 1. Okay, so it gives me 0 and 2 minus 1 1, and X and Y. Okay, so this should be equal to 0 0. This is a bit complicated, but okay. So from this part you can take that 0 into x is 0 plus 1 into y is equal to 0, which implies y is equal to 0. Okay, so from this part you can take 2x plus y is equal to 0. Since we already know y is equal to 0, so 2x plus 0 is equal to 0, and 2x is equal to 0, which implies x is also equal to 0. So when we get this x value and y value is equal to 0, which is basically all zeros. Oh, sorry. You should give me a definite number so that it will. Mm, of a. Okay. I took a wrong numbers here. But if you take right numbers, then if you take right numbers here, then obviously you will get the right answer. But I just took numbers in random, so I haven't got exactly the exact XY values that I need. Okay. I hope I haven't confused you. Uh, is it clear or anybody? Okay. What I want to cover next. Yeah. So actually, this is something that I wanted to cover next, but since you were asking null space, I just thought I'll just finish it off early. Okay. So the next part that I wanted to cover, the next part that I wanted to cover was linear equations. Can you please come in? Okay, if I keep repeating it the same thing, I might I may not be able to complete the whole thing. Okay, so let me just get back for now. But in case if time is sufficient at the end, if it's not 8 by then I'll definitely reply. Okay. Okay. So I wanted to cover linear. sorry, equations as well. So it's basically mathematics sentences declaring some equality between two expressions. So for example, like x plus y is equal to some value, a plus b is equal to some value. Okay. So the key characteristics is that the variables involved are raised to the power of 1, hence the term linear. So for example, if you look at it here, okay, I have something as y is equal to 8x plus 9. So the x here is linear. So it is not having any power at the top. So this part is a linear one. But when it comes to this, it has a square. Okay, so with this is not a linear one. If x is having a different power, let's say x power 3 x cube, then these are not linear. But in case if the power is only 1, then it is termed as a linear function. Okay, so imagine that you are on a road trip. Okay, you know the distance that you need to cover, and you know what your average speed is, let us say like 40 or 50, and then you wanted to calculate the expected time. So this is something that you have already seen when you were a kid, most in your mathematics books. So if a train is going this fast, how much time it will reach this particular station A or a station B. So using this formula, distance is equal to speed into time. So this is a simple example, but linear equations, it underpins the countless real world applications from physics to economics, and they are everywhere. So let's consider a more complex scenario. Okay. So let us say that you want to determine the optimal production level to maximize some profit. Okay, so this involves multiple variables and equations, and it's basically like a system of linear equations. So solving all these linear equations can be straightforward as isolating the variables, or it can involve complex systems with multiple equations and unknowns. So we'll explore various methods to tackle these equations. So we'll do sometimes substitutions to eliminations and matrix operations and etc. Sometimes you also hit and trail method. So you randomly give some x, y, z values, and you hope that those values will satisfy the equation, right? So it is like that. So let us say it's like it is represented as ax is equal to b. As I was saying earlier, if a is a cross n and x is n cross 1, then b is going to give me this m and cross 1. This will result in m cross 1, right? So we have different types, okay, in this. So I mean different kind of solutions that we usually find. For example, let us say a is equal to some 2, 3, 4, 5, 6, 7, 1, 2, 3. Okay, this is basically 3 cross 3. And if I have to multiply it with x, I have to take something 3 cross something. Let us say 3, 2, 1, 1, 2, 1. I have taken like that. Okay, it's 3 cross 3. If you can multiply these both, you will get some value with 3 cross 2, this 3 and this 2 as your final product. Okay, so why are we looking at these m cross n values and all of that? So if we are in m cross n, we can categorize it in certain ways. So we have 3 categories here. So if m equal to n, what happens? So the number of equations and the variables are the same. So this is the easiest one to solve. Okay. So it's basically like x plus y plus z equal to 1. Maybe x plus 2y plus 3z is equal to 3. 3x plus 2y plus z is equal to minus 1. So I have three variables here and 3 equations. So m is equal to n. Okay. So these are something which is very easy to solve for us. Okay. Then we have something called as m greater than n. So we have more number of equations. Okay, I'll just write number of equations and n are the variables. Okay, so in m greater than n we have more number of equations, and usually this gives no solutions. Okay, this is usually the case, but sometimes there might be some exceptions, but usually this is the case. We don't find solutions there. Okay, then comes m less than n. So the number of equations are less than the number of variables. Usually this has multiple solutions. Okay, so we can have a look at them as well. Also, before I go to that, I also wanted to tell you something. So if we are having this matrix equation, in this matrix equations we have three kinds of solutions. One is unique solution. So for the given set of equations, we have only one solution for that. Okay, we don't have multiple solutions, just one solution. Maybe x equal to 1 and y equal to 2, like that. That's it, and we don't have multiple ones. And then we have something called as consistent. Okay, this has infinite solutions. Okay, and then we have something called as inconsistent, and this is basically no solutions. Okay, so in this unique solution, this is usually the case when the determinant of A is not equal to 0 and A is a full rank. I'll tell what full rank is. Okay, and these happen when determinant of A is equal to 0. Oh, sorry, not determinant of A. No, sorry. When A is not full rank. Okay, so a matrix has full rank if the number of linear independent rows is equal to the total number of rows in the matrix. So number of linearly independent rows is equal to total number of rows in the matrix. Okay, uh, and this this one is for m equal to n, this part. Okay, so I'll stop sharing this and share my screen. Is it clear so far? Okay. Okay. Uh, as I was saying earlier, in case if you now let us come to our code. Okay, R Studios. So yeah, in R Studios, now for linear equations, I want to install a package called as MATLib. So if you don't remember how to give this part, like install.packages and in double inverted commas, you have to give MATLib. So the library that you want to use, you can either give it here or you can go to tools at the top. Okay, you can go to this tools part, and in tools you will be able to see this install packages. So initially for matrix I have shown there, so I just wanted to show it here now. Okay, again the shortcut to run just one single line is control plus enter. Okay, just give control plus enter, and then it will automatically install the package, whichever ones you have mentioned here. Okay, and also I have given dependencies is equal to true. So whatever dependencies are there on the whatever dependencies are there for these packages, all of them will also be installed. Okay, so once that is done, I will load the library. Okay, now I'll be good to go. Then, so first example that I wanted to tell is about a consistent equation. So consistent is basically having infinite number of solutions, right? Mm. Sorry, my art studio just wanted to download everything right now. Yeah. So, okay, let it download for now. So far, do you guys have any problem with art studios so far? Do you guys have any issues with art studios or using art studios, or if you want to know any shortcut or something like that? Okay. So I hope there are no issues with this, and have successfully stopped this one. So I'll just try to run it here. Okay. So now I'm taking a matrix of size 2 cross 2. Okay. So I'm taking the values 1, 2, and 2 and 4. Okay. So yeah, let's run that part. And then I'm taking b is equal to 3 comma 6 as another vector. Okay, so if I show the equation, you can use this function called as show equation, show eqn. And if you want to know more about its functionality, then you can actually give a question mark and write this, so show equation. Please bear with me until this actually loads. Rank nullify theorem. Yeah. So rank nullify theorem is nothing but, okay, just show here. Sorry. So as you can see, you take the rank of the matrix that you have, and you also take the number of columns of the null space of that particular matrix, and then you add both of them together, and it should give you the total number of columns of that matrix which you have taken initially. So let us say I have taken a matrix A, and the rank of the matrix is maybe 3. Okay. And then the number of columns in that null space, assuming that the null space does not exist, so which is basically 0. Now if I take it as 3 plus 0 is equal to 3. Okay, and this 3 is nothing but the number of columns of the matrix A that I have taken. Okay. Am I clear, or do you want me to explain that in writing? Cool. Um, This is taking longer than expected. I actually uninstalled everything so that I can show you guys during the class, because morning it was super fast. I thought I could just show it so that you'll be clear on this installing and stuff, but then it backfired terribly. I am so sorry. You want me to repeat the rank nullify theorem? Just give me a second. Okay. So let us say I have a matrix called A. Okay. Uh, and that is of size, let's just say 3 cross 3. Okay. So let us say I have tried to find the null space. If you haven't, if you weren't there for null space, I have explained it earlier. So later, if you want, you can just this recording will be posted, so you can just go back and check it again. Okay. So as I was saying, so you have this null space. Okay. Uh, it will be some a vector. Okay. uh, let us say 3 cross 1 or something like that. Okay. So according to the rank nullify theorem, which means that the rank of this matrix A plus the number of columns of this null null space should be equal to the number of columns of A. Okay. For example, if this is giving, just let us say if this rank is equal to 3 and the number of columns is also equal to 3, then I can surely say that the number of columns of this null space is equal to 0, which means the null space does not exist for A. In case if I say the rank of A is equal to 2, uh, okay. if I say the rank of A is equal to 2 and the total columns of A is 3, which is fixed, okay, then I can say there exists null space and the number of columns of that null space is equal to 1. Okay. Is it clear now? So last week there was some problem with uploading the video on YouTube, so I was a bit delayed. So by tomorrow you will get this video link again. Okay, so just in case if anyone wants to look back at it, you definitely can do it now. Okay, by tomorrow afternoon I will definitely give that, and also this code also will be shared on the drive link. Okay. Also, okay. So since we already have some time, do you guys want me to cover any other topics in the next week? In the next week, if you want me to cover any topics, if you can just tell me now, I can prepare those as well. Because some people have sent me emails asking if they can, if I can explain some certain things of that week, but I haven't explained during the these sessions, problem solving sessions. So if you need something, you can just tell me now and I can do. And with respect to where to find drive link, I hope NPTEL admin has sent that drive link to everybody. If not, I'll just send it to you. Yeah. Okay. At the end of the class, I will send. My laptop is hanging. At the end of the class, I will send. Okay. So this is good. Everything is installed. I'll share my screen again. Thank you so much for bearing with me. Now this package has been installed. Okay, ready. And then, yeah, as usual, I'll go through each of the matrix. It's still loading. Come on. Yeah. Okay. So I have this matrix A and I have this matrix B. Okay. Now I want to see the equation. Okay, then I'll use this function called as show equation, which is from this library MATLAB. Okay, then we'll just run that and then we'll get this equations here. Okay, 1 into x1 plus 2 into x2 is equal to 3, which is nothing but ax is equal to b form. Okay, so I want to see the ranks. So initially, as I was telling, m equal to n or m less than n and m greater than n, we have to check those first. And once we check those, then we can go to the next part. Okay, then we can check the consistency as well. I have the rank of A is equal to 1 and the rank of A and B together is 1. Okay, so which means is m is equal to n. Okay. So for checking the consistency, I'm using all dot equal. So basically checking if if both are equal or not. Okay. So I'm checking it and it gave me the answer as true. Okay. So this is all okay. Now I want to plot the equation. Okay. I have plotted the equation. So if you can see here, both the graphs are overlapping on each other. Because if you see it clearly, I have given the matrix as 1, 2 and 2 and 4. So 2 and 4 is nothing but multiplying the first row with 2. So which is basically the same equation I'm giving with just with just multiplying it with 2. So basically the graph is going to be the same, and from the beginning till the end all the points are going to lie on each other. So I'm going to have infinite number of solutions for this one particular value. Is it clear? Can you guys see the plot here? So I have plotted the graph when both the lines are on top of each other. So it is having infinite number of solutions from the beginning till the end. Okay. Uh, so this is a consistent one, which means that it is having infinite number of solutions. Okay. Show equation. Okay. So show equation basically this AB is nothing but AX is equal to B form. Okay. Not this one. Sorry. This X is equal to B form. Okay. So this X is nothing but X1 and X2 here. So I have it like X1 plus 2X2, 2X1 plus 4X2 is equal to 3 and 6. Okay. So just look at the first equation, just the first equation, and multiply that first equation with 2, which is actually giving me the same thing. Okay. Now, if I am going to plot both of them together, it is nothing but the same graph, just multiplying the values with 2. So from the beginning till the end, I'm going to have all the solutions to be the same. Okay. This R of A is nothing but rank of A, and this R of C bind AB is nothing but the rank of A and B. Okay. So first we are seeing the ranks of both of these values, and then we are checking if both of them are equal or not. So initially when I was explaining the theory part, I was saying m equal to n, right? Same way. I am looking if these two values are equal or not, and then I'm plotting the graph. Okay. And now I'm using this solve function to show me the solution. So this is going to have an infinite number of solutions, so it is not going to give me anything. So it is just basically giving me 0 equal to 0, and any values that solve this x1 plus 2x2 equal to 3 is the solution for it. Okay, so that is what it means here. Okay, so this is for consistent part. So now let us look at unique. Unique means it has only one solution. Okay, so this is a matrix that I'm taking 1, 2 and minus 1 and 2. Okay, and this is matrix B. This is also of the form AX is equal to B. Okay, and I want the equation to be shown here. X1 minus X2 is equal to 2 and 2X1 plus 2X2 is equal to 1. Okay, now similarly again I'm going to check for the ranks of A and also the rank of A and B combined together. I have got both of them to be the same, so m is equal to n. Okay, now I'm checking if it's equal or not. Yes, it gave me true. Then now I'm plotting the equation. Okay. So when I plotted the equation, see one graph is like this, one graph is like this. Okay. So once this is done, we have a point of intersection here. So this point of intersection is the solution for these equations. Okay. So just like that, let us have a look. So this is almost near 1, but greater than it. And for x2, it is a bit less than 0. Okay. So if we solve, what will we get here? So we are getting x1 is equal to 5 by 4 and x2 is equal to minus 3 by 4. Okay. So this 5 by 4 is a bit greater than 1. So if 1 is here, it's a bit greater than 1, and it is a bit less than 0 and minus 3 by 4. Okay, and here I'm giving fraction is equal to 2, and in absence of this, these values are going to come as decimals for me. Okay, so that is the only reason I give fraction equal to true here. In case if I don't give fraction is equal to 2, then by default it is going to give me decimal values instead of fractions. If I want to have a look at it in fractions, then I'll give this. Okay, hopefully I'm clear till here. After this, code will be available on the drive, and the drive link has already been shared by NPTEL team with you, I guess. Also, it will be there in the problem solving session for on the left side of the NPTEL course portal. If you see on the left side, you will see the problem solving sessions part. There itself also it will be. Okay, in that I will eventually add once the class is done. Okay. And then yeah, if you solve it, you will get the equations here. Let us just remove the fraction and see how it is. Here we are getting it as decimal. Okay, now let's go for some inconsistent equation. Inconsistent equation means the equations that does not have any solution, so it's basically no solution for it. Okay, I am having two matrices, C and D. D is a vector, and I'm showing the equation here. X1 plus 2x2 is equal to minus 3, and 2x1 plus 4x2 is equal to 6. Okay, then now I'm checking the ranks of both of them, and I'm not getting the equal ranks. Okay, I'm getting one rank as 1 and the combined rank as 2, which is not equal. And here, when I asked if it is equal, it is telling me that there is a relative difference of 1 between both of the values that I have asked for. Okay, so now let's plot the equation and see how it is. As you can see, these two are two parallel lines and not at all intersecting at any point. So basically it has no solutions. But just out of curiosity, I have tried it for solve. Try to solve it and to see what kind of answer it will give me. So it gave me this answer. One is the exact same equation, not same, but yeah. And the second one, it is showing me 0 is equal to minus 6, which is not possible, right? So which means that there is no solution for this particular two equations that I have taken. Okay. Similarly, you can also try for three consistent and inconsistent equations. Okay. So now let's check for three unknown variables instead of just two. Okay. Um, I have this matrix of the size 3 by 3. Okay. And with an example. Okay. Um, when I say that there is no solution for the two equations, which means that as you can see in this graph here, these two lines are never going to intersect with each other, which means that there does not exist any value that satisfies both the first equation and the second equations, which means x1 and x2, like if I so the both the equations to be solved, I should have a value x1 and x2 such a way that it satisfies the first equation and it also satisfies the second equation. Okay, but since these two lines are parallel, if you can see in the plot, it means that there does not exist any x1 x2 values where both of these equations are there, are satisfied. But if you see this unique solutions plot, right, I'll run it once again. So if you see this plot, I'm having two equations and both of them are intersecting at one point. So if I take these values and put these values in this equation, it will it will satisfy this first equation. If I take this value and I put it in this equation, it will also satisfy this equation. Okay. Is it clear? Okay. Yeah. I have taken this and okay. And I have assigned some column values stating like x1, x2 and x3. Okay, if you want to have a look, here it is. Okay, so I'm having x1, x2, x3 and I am assigning it to this matrix. Okay, if you want to look at the matrix here. Okay, and now I have another b value. So since we have increased the matrix size from 2 cross 2 to 3 cross 3, the b value also increases. Okay, so let us see the equation now. So here now we are having three equations and three unknowns, right? Let's look at the ranks. So basically the a gave me 3 and the combined rank of a and b also gave me 3. Okay, so let's directly go for solve. uh, so this solving it gave us the values x1, x2, x3 as 2, 3 and minus 1. Okay, if I want to have a look at it in a matrix form, then I can use this. Okay, solve A and percentage symbol and multiplication and again percentage and then give B. Okay, I got it like a matrix. Not matrix here, it's a vector. Okay, another alternative instead of using solve is you can use inverse A and B. Okay, so as you already know, ax is equal to b, and if I want to find x value, x is equal to a inverse b, right? So that is exactly what I'm doing here. Okay, I'm taking an inverse of a and then I'm multiplying it with b, and I'm also getting again I'll get the same value. So in case if you don't want to use these and you want to use a different alternative approach, then you can go to echelon form. Okay. So then it will directly give me these x1, x2, x3 values. So this is an identity matrix 1 0 0 0 1 0 and 0 0 1. Yeah, it's a beginner program only. It's just basic matrix that I'm showing. Okay, and yeah, you see the identity matrix here in this part, and then you can see x1, x2 and x3 values here. Okay. So if you want the full entire thing, like step by step, like how this is attained, then you can give it this way, echelon and verbose equal to 3, equal to true. And then you will be able to get the entire thing, like what is the procedure that you have to follow, like exchange the rows and multiply the rows. All of these will be given to you. Okay. So yeah, so once that is done, you can plot the graph. Okay. So for plotting, initially we were just plotting it normally like plot and we are giving A and B. But now since we are having three equations, we are going to plot not lines, but we have to go for planes. Okay. I don't think this is visible, right? I have to shift. Just give me a second. Can you see the plot now? Can anyone confirm? Yeah. So as you can see, we are having three planes of all the three equations. So since we are having three unknowns x, y and z, we are going for plane. If we are having only two unknowns, that is x and y or x1, y, x2, then we'll go for just the normal plot, x and y axis cup type of plot. So since we are having three here, x, y, x1, x2, x3, we are going for this plane part. Okay. So if we look at it closely, there comes a point where all the three planes are intersecting. So that is the basically the solution of this particular matrix. Okay. So clear here. Okay. Anyways, I'll continue. Then I'm going for inconsistent type of equations. So inconsistent means which there exists no solutions for all the three matrix, or I mean all the three planes. So let's this is the same thing, just the values are changed here. Okay, again I'm checking for the equation and checking for the ranks. Now the ranks are totally different. The rank of A is 2 and the rank of combined A and B is 3, right? Then I'm checking if all are equal or not, but there is a relative difference between that this rank and this rank. It is showing. Then I'll ask it to solve, but it is not going to solve me anything because there does not exist any value there. Okay. Where did you plot that earlier plot from? Here, here. So plot equation 3D. Okay. Yeah. Cool. Okay. So far clear. Okay. Now I just want to go for orthogonal part. Let me just share my screen. Okay. So these all are. So these codes will be shared with you guys. So you can also keep changing the values that you need, and you can have a look at it. Okay. I'm not deviating from the syllabus. This is the same syllabus that has been taught theoretically in the class, and I'm implementing the same thing uh, in R. Okay. Just give me a second. Okay. So can you see the screen again? Okay. So let us say x is a data point. Okay. And then we have and we are representing x as x1 and x2. Let x1 and x2 be the distances from the x1 and y1 axis. So if I say this is x1 and this is x2, there is some data point x1, x2. Okay. So the distance between these is x1 and x2. Okay. Just like x and y, how we represent the same way. Okay. So if I want to know what is the distance, the formula for that is from the origin. Okay. So that is nothing but x1 square plus x2 square and square on top of that whole square root. Okay. So in case if I have two data points, okay, one is x1 dash comma x2 dash, another one is x1 double dash and x2 double dash. If I want to know the distance between both of these, then L is equal to, so one value minus another value. It can be anything. It can be x1 dash minus x1 double dash or x1 double dash minus x1 dash. So both are going to give me the same values, x1 dash minus x1 double dash whole square plus x2 dash minus x2 double dash whole square. Okay, so these are the distances. There are many types of distances. So this is just one form of distances. But if you want to have a look at more types of distances, then what you can do is try this. In R, you can try in the console. Okay, in R console, give two question marks and type distance. Okay, all the different type of distances you will be able to see there, and you can also give some x1 x2 values just for fun, and you can try all the different types of distances and how it varies from one type of distance with another type of distance. Okay. The next one is a unit vector. So unit vector is nothing but making the magnitude is equal to 1. So if I'm taking this magnitude of A, then I have to take the matrix A divided by the determinant of that matrix. Okay. So yeah, if I'm taking A is equal to 3 divided. Okay. Okay. Are you clear so far? Okay. Okay. So the next part is orthogonal matrix. Orthogonal vectors. To say that two vectors are orthogonal to each other, the dot product of both of them should be equal to 0. So that is, so if I'm having a vector A, okay, of maybe size 3 cross 1 and a vector B of size 3 cross 1, I have to multiply both of these to get the value 0. Like if I get the value 0, then I can say A and B are orthogonal to each other. Okay. So yeah, if I take the 8 now, this is of 3 cross 1 and this is of 3 cross 1. I cannot multiply A and B directly, right? I can't take the product of A and B directly because the value here is 1, the value here is 3, which are not equal. So instead what I do is I'll take A transpose. Okay. So this will make it as 1 cross 3. and B is already 3 cross 1. Sorry. These two are already same. So now I can take A transpose B. I can take the product of both of them, and then I'll get some value. That is 1 cross 1, right? So that is about orthogonal vector. So I'll just show the code, okay? Stop this one. Is it visible? Uh, Two planes. It means that they are at 90 degrees to each other. Okay. Okay. So yeah. So if I'm taking the orthogonal matrix. Let us say I'm just taking two random variables. Okay. Is it clear? What orthogonal means? Orthogonal means like they are at right angle to each other, 90 degrees. Okay, great. So yeah, we have two vectors here, v1 and v2, and I have taken some values to them. Okay. Now, as I was saying earlier, I need to take A transpose B, right? So I'm here. This T represent transpose, and T of v1. So transpose of v1 multiplied with v2. So if this v is equal to 0, then it means that it is orthogonal, right? So I'm printing v and I got the value as 0. So which means that these two vectors are orthogonal to each other. Okay, if you want to look at it, you can also plot both of them together. Okay, which you can do by yourself. Let us, for example, just for fun, let's change the value here and see how it works. Now I got v value is equal to -2, which means they both are not orthogonal to each other. Only if the value is equal to 0, then it is orthogonal to 0, else it's not. Okay. Also, I have added some more extra part here for the distances, calculating the distances. So I have taken some random vectors, okay, A, and I'm binding all of them together as a matrix. Okay, if you want to see the matrix, so basically I'm binding all the vectors together now. Okay, now I want to know the distances between each other, and I have used a method called as Manhattan here. So as I was saying earlier, so in distances you have different type of methods, and Manhattan is one such type. Okay, so I'll just run this and I got these values. So which means, so the distance between A and A is 0 because both are the same points. The distance between A and B is 3. The distance between A and C is 6. And similarly, B and A is 3 again. You will see the same things. And the distance between B and C is 5. Is this matrix part clear? Okay. Okay. Uh, just a second. So then let's go to orthonormal vectors. So orthonormal vectors are the vectors that has the magnitude 1 and the set of vectors are orthogonal to each other. Okay. So I'm taking two vectors v1 and v2 from before, from here. Okay. these two v1 and v2 values. So we already clearly know that these two are orthogonal to each other, right? So I'm taking those two values again. Okay, so you don't need to know all of this part. This is just for seeing purpose. Okay. Uh, so I just wanted to show this. Okay. So this is nothing but you were seeing earlier, like to get a unit vector. So we are taking the vector. So we are taking a vector and then we are dividing it with the magnitude of that vector, right? So the same way I am doing it, and then I'm combining both of them together, and then I'm checking if it is orthogonal or not. Okay, and this is an orthogonal matrix. Okay, this is just for you to visualize, but nothing important. Okay, then I'll quickly cover eigenvectors and eigenvalues. Okay, so I'll come back to it again. So the theory part. So I'll finish up this. So if I want to find the eigenvalues and the eigenvectors without using pen and paper, we can do it on R. So now I'm taking a matrix, okay, of the size 3 cross 3, and I want to visualize a matrix. Okay, and this is the matrix for me. Okay, then I have applied eigenfunction to it. So this eigenfunction has two types, values and vectors. So it will give me the eigenvalues. I'm going to store values in this values function. So okay, sorry, values variable, and ev is this, and in eigen it will give me values as one of the output, so a dollar symbol and values. Okay, I'm storing the eigen values in this part. Okay, so these are my eigen values for this particular matrix. Okay, so if I want to look at eigen vectors, then I'll do the same, but in place of values I'm going to give vectors. Okay, so there are some properties of eigenvalues and eigenvectors. Okay, and I wanted to verify them. Okay, so these are the properties. The first thing is the orthogonality of a dash and a. So if I multiply a dash and a, I will be getting an identity matrix. As you all know, identity matrix means everywhere it will be 0 except the diagonal. Diagonal values will be 1, but remaining elsewhere everywhere it is 0. Okay, so a dash and a is equal to I. So I'm taking the cross product of both of these values, both of the vectors, and then I got some values and which are very small. So I'm using this function so that everything will be rounded off to zeros and ones. Okay, so this is all just for information only. Okay. And then the second property is that if you take a trace of the matrix, trace means all the diagonal in the diagonal whatever elements we have, the sum of all those elements. Okay, so the diagonal matrix, the trace of the matrix is equal to the sum of all the eigenvalues. Okay, I want to have a look at the trace of A. So I'll just do that. I got the trace as 32. And now if I want to take the sum of all the eigenvalues, still I got 32. So both are the same, right? So that property is also verified. The next property is sum of squares of A is equal to sum of squares of eigenvalues. Okay. So I'm taking the sum of all elements of A square, and then I'm taking the sum of all values square, and I'm getting both values as 402. Okay, so that property is also solved for me. How? Yeah, So that is not exactly 5.3 and all. So if you can look here, it is e minus 16, which means 3.05 into 10 power minus 16. So which is like where 0.00000 and after some time then 3 comes. So which is almost close to 0. Am I right? So for that reason, I just wanted everything to be rounded off to the nearest number. So I have used this zap small, so which will round off everything to 0 and 1. Okay. If you look at the first one, it is 1 into e power plus 0, which means just 1. But these values are very in decimals, but in the power of 10 power minus 16 and 10 power minus 17. So I just wanted everything to be rounded off. Okay. Yeah. So determinant. So the fourth property is that the determinant is equal to product of eigenvalues. So we'll see the determinant of A, and then we'll see the product of all the eigenvalues. Okay, I got the same values 952 and 952. Both are the same, right? And the fifth property is that rank is equal to number of non-zero eigenvalues. So again, I'll check the rank of that matrix. I got the rank to be 3. And then I want to check the sum of all the non-zero eigenvalues. So values not equal to 0, I'm giving that as the condition. And then here I go. I got some value. And this is another property. Okay, but I haven't added here because it is way too complicated and I didn't want to confuse. And it's a pretty long code. Okay, uh, so that is all from the R code side. Okay. And previously I just told I will also cover eigenvalues and eigenvectors theory part, right? So most of it has already been covered in the lecture series. So you can cover most of it there. But in case if you have more doubts, you can also ask me later. Okay. And if you have any more questions, you can post it on this forum. Okay. I hope you all are aware of the forum by now. So you can also use the forum to ask your questions. Okay. What's the use of determinant? So previously, as I was explaining, um, just show here. Huh. So can I share this one? Are you guys able to see? So there are some different types of uses of determinant. So for example, if you are looking at the number of solutions that exist in this matrix equation, if you look at the unique solution, uh, the first there are this one. If you look at this part, okay. So this is one of the conditions we look at to make an assumption what kind of a solution that we are having. If the determinant is not equal to 0, then it may be a unique solution. It may be not 100%. Okay, we should also look at a different condition for it to be a unique solution, and this is one such criteria only. Also, if you are calculating A inverse, okay, if your determinant is equal to 0, then you may not be able to calculate that A inverse, right? So for such things you can use the determinant. And yeah, someone was asking for drive link, right? Okay. So I have sent the drive link here, and the drive link is also available on the NPTEL portal itself. So you can have a look at it there as well. Okay. Also, if anyone is having any problem with our studios, just do let me know, and I can help you now itself. Also, is there any topic that you guys want me to cover in the next session so that uh, I can prepare beforehand and come back to you guys? Important libraries. Um, so as we go, we keep using some libraries. For now, you can use this matrix library. Okay. Matrix, and then you can also matlib. So these are the two libraries that we have used today. Okay. Similarly, if you want to use data sets, like already existing data sets on our you can use data sets library, which was used in last week. So that library, like you can have a look at it in the last week's code. Okay, that is also there on the drive. So as we go, we keep using new libraries. So it won't take much time, but today it just Matlib took a lot of time. But rest of them are pretty simple and pretty easily downloadable, and you can install. Okay. Week two. Uh, just a second. Week two lectures, whatever discussed in videos, when will we get those PPTs? You meant week two lectures as in NPTEL lectures which were taken, or this one? Can you just clear that out for me? If you can focus teaching us R from application perspective, like giving it. Oh, yeah, yeah. So that is exactly what I wanted to do as well. Like giving some. Okay. So basically, I can't stick to one particular application here, but when I was teaching the theory part, I was trying to get some real life applications, like some real life examples, so that you guys can relate to. So that was what I was doing for the theory part. But when it comes to the code part, I don't think it is really nice if I can stick to one particular thing. For example, I work in biomedical area. Okay, I work on images and all the volumes and other stuff. Okay, so if you ask me, I can focus on that. But what about the people who work in a different area, for example, some mechanical systems or something like that? So again, it will not be relatable to them. So I don't want something to be and this course is definitely not application focused. So it is in general. So I'm trying to take just random numbers so that it will be easier. Okay. Uh, so you wanted to see the NPTEL, okay, the NPTEL lectures. So if you go to the NPTEL website itself, on the left side, you will see something called as transcripts, if I'm not wrong. Just give me a second. Yeah, text transcripts. You will have it in different languages, starting from English and Marathi as well. So all of those will be there. So you can go there and you can click on download, and another drive link will open. And in that drive link, you will have all the documents in lecture wise, lecture one, lecture two, and all of that. Okay. Thank you so much. Thanks a lot. That really means a lot to me. Okay. And this is my first time I'm teaching online, so it is very I, I'm very anxious sometimes in between, but thank you for your appreciation. Okay, any more questions? So we still have 5 more minutes left. If you have more questions, I can answer, and if you want me to cover any other topics next week, I can also do that. Yes, yes. I will add my notes. I'll add this code. Both I will add in the drive link. Okay. So the folders will be created according to weeks. This is since this is week two. I'll create a folder with the name week two, and I'll add everything. How to install packages. Um, okay, I'll just share the screen again and I'll show. Um, so to install the packages, you can go to this tools at the top, and here you have the install packages part. Okay, if you click on that, you can type in the package that you want and then directly click install and everything will be done. Okay. Or if you want to install the packages through code, then you can also do it this way: install.packages, and you can give the package name. Okay. um, are there any more questions? By 8 I will stop if there are no questions. But if you have no more questions, thank you for joining, and this is the end of the session. But if you have questions, you can post it. I can explain. The video recording will be posted by tomorrow afternoon, and also these things will be given in Drive. Okay, the notes and the R code both. Last week I haven't written any notes. I have only made a PPT, and I have already added that PPT in the Drive link, and the R code was also there in the Drive link. Okay, thank you. Thank you so much. Thank you so much for listening to me. Okay. Uh, I'm not sure. I'll check and I'll get back to you. Okay. Or you can just post about this on the forum, and another course TA will answer that. Yeah. Okay. Thank you for joining, everyone. Good night.